Okay, it's coming up. Okay, we're on live now.
Okay, great. Thank you.
you.
Okay, so welcome back to all the students. Today, the second part of the lecture that was started past week is again about gamma ray astronomy, but with a focus more on the instruments that are making this detection possible. I have to tell you that, well, that's the program, but I will skip about this. I have two disclaimers. The first one is that I took many slides from, well, some slides from a presentation by Razmik Mirzoyan at a school that we organized like 2 years ago before the COVID. You have the link there, and you can find, if you're interested, you can find more slides on instruments and more focus on really gamma ray astronomy, not for the dark matter part, but in general. You can click there. And the other, it's an apology that I couldn't really follow the school through the days, because with these Zoom meetings at the end, I have to follow duties here in Padova, and I couldn't really check the interesting program, and I'm very sorry for that. Okay, this slide was already shown. So we were discussing past time about the amazing cosmic ray spectrum. We were saying how complex, well, how regular, but at the same time, how complex is the spectrum, how many particles are there, from protons, from ions, from features like the knees, double knees, the ankle, the cutoff. We were discussing about electrons and positrons. You may remember diffuse gamma rays. And this bottom part here, extremely exciting, in which you say that the diffuse photons, neutrinos, and cosmic ray flux, it's kind of at the same energy flux level, which make these three messengers connected. We were discussing how gamma rays play a role in these cosmic ray searches, and how important they are, because they trace back the point in which they were produced. And this is an amazing image from Fermilab. There will be more talk specific on Fermilab during this school, so I will not spend too much time here. But still, we're tracing here not only the astrophysics, but also the cosmic ray physics. And when we look at a point, we look what's happening at the particle physics point very far away from us. We also we're discussing that there are big differences. For example, here you have really a full sky map. Here, when you look with the TV instrument, you just see few points because of several things that we will also be discussing today. So we do not have the same performance at all the energy, and that's something we will discuss today in more details. We saw last time how really the picture is becoming more interesting in the past years, from 2017, in which we had the connection between gravitational waves and gammas. Next year we had the detection of neutrinos together with gamma rays. So our pictures is becoming really a whole picture, and we can plot information from a source, from really the radio waves to the gamma rays, and now adding also neutrinos, if you remember the past lecture. This is happening for extragalactic sources, for galactic sources, and you remember here the imprint of the connection between gamma rays and cosmic rays. This peak is the synchrotron peak, so the electrons that are accelerated, and this peak is the inverse Compton peak from the same photons emitted by synchrotron radiation up scattered to TeV energies. You remember the two main mechanisms that we were discussing past week about the inverse Compton here, and the pion decay in case you have primaries that are hadronic. So how do we detect all these gamma rays? What instruments do we need? The first thing is, again, a recall from past week, is that we kind of have a certain classification of gamma rays and cosmic rays, okay? So we call low energies those gamma rays and cosmic rays below 30 MeV, okay, in which the only technique is the Compton effect. We call high energy gamma rays those between 30 MeV and 30 GeV, roughly, okay? This is not a hard classification. And there you have to go through satellite. We will discuss this, like Fermi, in which you can start to have calorimeter measurement because you have reproduction. We have a very high energy now from 100 GeV to 30 TeV, and so on. We have ultra high energy and then extremely high energies. Okay, and that's what was discussed past week about the classification. Now, what is the problem? Okay, clearly, okay, you cannot have an instrument that takes from radio here, this part, to optical, to X-rays, and here is the gamma ray part. But even here, if you look at the spectrum here, it is not conceivable to have one instrument. Just look at the steepness of the spectrum, okay? You have 2 orders of magnitude in less than 1 orders of magnitude, okay? Or even more. So at the end of the day, your signal is something that has a photon index, let's call it, which is -2 to -5, okay? So you have 10 to the -5 events if you multiply the energy by 10. It's really hard to get to have an instrument that is sensitive for such a large energy range. Okay, so we need more than one. Okay, it's not available an instrument that can do everything alone. That's an important point to start our discussion. Because I want to give you some messages. I'm not familiar with you. Unfortunately, we didn't meet during this conference, so I don't know about your background, but I would like to leave you some messages. So the other point is not only that we do not have a single instrument, but then when you have, if you want to learn gamma rays, everything below, okay, gamma rays from X-rays down to radio, you can reflect them, okay? Maybe you didn't think about it, but anyhow, reflect them means that you can concentrate them, okay? So you can build instruments like this, in which you really have a wide area and you focus all your signals well, from the dish to the camera, okay? And this can be done, of course, in optical. This is how it all started. But then it went down to radio, and it can be done in UV, can be done in all these bands. But when you start, it can even be done in X-rays. If you do something different, like grazing incidents, you use the reflection that at the maximum angle. But then when you start to have that much energy, you cannot really reflect gamma rays. So you cannot concentrate gamma rays. That's an important point to start with, because you start interacting with the matter, and so you have to use other means like Compton scattering, pair production, and then the production of Cherenkov light in air. Okay, I will. This is the focus of this talk. Okay, so this is familiar probably to all of you in function of the photon energies. When you start having photons of very high energies in the gamma ray band, you start first with the photoelectric effect, and then you enter into the Compton process, okay, in which you transfer energy to the electron. And finally, you have basically just pair production. The energy is too much, and what you have is the annihilation of the photon into an electron and positron pair. Okay. So this will guide us a little bit into the knowledge on how you have to build the detector. Okay, if you want to detect KV, okay, you don't have pair production. You have pair production if you want to detect 1 GeV or so or above gamma rays. Okay, and whenever you want, you can interrupt me, of course. Okay, now let's try to relax a little bit and spend some time on these things that I was that I was discussing with you. So that's a plot of sensitivity, okay, in a certain, that's energy in energy flux in function of the energy, okay? And you see that the things that I was saying before, it is very hard to find an instrument that covers more than 2 orders of magnitude. Okay, you have these ones here, 2 orders, 2 or 3 orders of magnitude. This one, it's more, but it's because it's kind of 2 instruments at once. Egret, Fermilat. This is a sensitivity, but you see that here it is much less sensitive than here. Okay, so you have to focus on the main part here in which the instrument is really sensitive. Okay, so that's the first message, and that's why you need to have that many. Okay, this is all gamma rays from MEV or fraction of keV to TeV or so, and you have to have many of them. Now, that's a nice collection that you can find in this archive here. This is was produced for this instrument that I will talk about. And you see also that there is kind of a vertical change of range. Okay, so you may wonder that it's better to be on the low side. No, that means that you can detect lowest fluxes. That's why these are not all instruments that are existing. These two, for example, they're not taking data anymore, Comtel and Egret. They are on the top part. But these are many, and these are still there. Some are older, some are newer. But anyhow, Hawk, Lasso, High Score, Magic, Fermilat, Integral Instrument, these are taking data now, okay? And at the same time, we will have, so this is a mistake, GEMX is on Integral. We have instruments like eAstrogram and CTA especially, which are the future. This is not complete, there will be more instrument. It's just a glimpse on the fact that constantly we have to cover the full energy range, okay? And we have to try to go down as much as possible with our sensitivity, okay? Today I will really discuss about few of these, well, as much as possible of this instrument here. I have to make an important remark here, okay? This is a plot of sensitivity, and sensitivity is really what you want. It's the minimum flux that you can detect, and you want to be as much sensitive as possible, okay? But for you, especially if you're not in the field, or if you work on other fields, or if you're not an experimentalist, it's important that you understand that sensitivity is not the only thing that matters to judge an instrument, okay? Clearly, the sensitivity range is important, how much is sensitive, but it's not the only factor. For example, you remember from past week that we have sources that are really changing their flux level, okay? Not throughout the year, but we saw last week that we have sources very far away that are changing, that are doubling the flux in 2 to 5 minutes, okay? It's really what is called a transient event, okay? Something that is really changing. We only briefly discussed past week that you have gamma ray burst, in which there you have seconds, okay? The flux is huge, but it changes in a matter of seconds. This means that you want to be sensitive not only to a certain flux, but also to the variation of the flux, okay? So now, for example, if you compare, this is again a sensitivity plot. This is energy, this is differential flux, and this is an Hess and CTA, maybe you know the names. This is the sensitivity range here, and this is lat. Okay, so different energy band, but you may see that here CTA starts to be better, but in this range here, Fermi is much better. Okay, but now if you look more closely, you see that here is written 10 years, and here is written 100 hours. Okay, or 1,000 hours. The sensitivity here is computed on the steady flux that would be observable for 10 years, and this is for 100 hours. Okay, so it really changes if you have a varying sources. Here for comparison, you have the Crab Nebula flux, you have the inverse Compton peak there. Anyhow, okay, so that's the sensitivity. Just because I will use this plot later, you see that we will discuss why here is better than here and here, why it's shaped like a U. Now, if you now put the sensitivity in function of the integration time, okay, so this is a very short event, just for 10 seconds, and this is for many more seconds, like 10 years is here. You see now that, and this is again the sensitivity. So one instrument, CTA, is very sensitive to short burst, okay, instead of Fermi-lat, and only in case of very steady fluxes, you have this comparison here. This is very hard to judge if you don't know the instrument. So it's really important that we start seeing what are the figure of merit of an instrument, okay? So there is sensitivity, but the sensitivity is in function of the integration time, of course. Another fact that is really important is the energy resolution, okay? Now look at here, for example, I will steal some slides from Magic. So this is energy, okay? We are sensitive of photon from 100 TeV to 100 GeV, but the energy resolution is not the same. So when we observe a photon at 100 GeV, we make a mistake of 30% every time. We don't know, we cannot do much better. This is going down to 10 or 5%, okay? When we reach the 1 TeV, this means that the instrument is working better in this range than here. You say, well, who cares about this? Well, if you're looking for, we know, okay, that we have the crab here with several spectral features, and you know dark matter that has several spectral features. If you don't have sufficient energy resolution, all these cutoffs and peaks, they are smeared, okay? So you detect the flux, but you do not really understand what's happening there. So energy resolution is with 1 point. The second is the angular resolution, okay? Angular resolution is clearly the capability to discriminate photons from close angular distances. And again, you see, well, that's for CTA. You see that between 1 and TeV is where CTA was better. You have a 0.05 degree containment, which is decreasing pretty much to 30% at low energy. So if you want to detect something at low energies, you cannot do very well the morphology, okay? Something that is smaller than your angular resolution here in this part here is called point-like. But it's not point-like, it's point-like for you, for your instrument, because you cannot detect its extension. For example, here, if you look at something produced in gamma rays, you see that you always have the reference PSF. The PSF is kind of this line here, this radius here. And you can see from here, you can judge by your eyes that this is a slightly extended source, okay? So it's important to have angular resolution if you have an object that you need to know the morphology. For example, for dark matter, if you want to discriminate between a core profile or a cusp profile, sometimes you need to have angular resolution. Another ingredient is the effective area. The effective area, these are two arrays, so here is, you have saturation and when you have 100% of efficiency, okay? This is, you can call it efficiency. So you have 100 gamma rays here, and you detect 100 gamma rays. 100 gamma rays reaching the instrument at 10 TeV, and you detect all of them. That's 100% efficiency. and then you multiply by an area. This is a convention. But now you see that if you go toward lower energies, like 1 TeV or 100 GeV, your efficiency is not the same, okay? So here, you can say that by this, not that more or less, every 100 photons that reach your instrument at 100 GeV, only one you detect. And that's because, we'll see maybe, but that's because of the instrument and what you're looking is not a defect that sometimes you can correct. But here, by this, for example, we can learn why we have this shape, okay, in the sensitivity. I'm not sure if I'm saying something very naive for you, but really this part is where you are most sensitive, is this part here, okay? You are as efficient as possible, 100% or 90%, I don't know. This is your best performing part of the spectrum. Now here, okay, you start to be less efficient because you detect less photons, okay? And normally you maybe do not expect this because you have much more photons at low energies than at high energies, okay? Still, because you are not able to reconstruct them, you are not as sensitive as here. And this is happening here and basically in every experiment. Now, okay, I hope this is clear. Why are we losing sensitivity toward when we increase the energies? I don't know if I can make a question. Does anybody knows why the sensitivity is getting worse to when we go to higher energies?
Because there is a less number of photons.
Exactly. Good. So here we are really having less and less. We are having in maybe 2 orders of magnitude 2 orders of magnitude in energy means maybe 4 orders of magnitude in photons. So we have 1,000 of photons with what we have here. So we have a loss of sensitivity. Okay, so these are, but the reasons for this to be worse here and here are completely different. Thanks for the answer. Thanks for talking about this. Okay. The other point when we compare experiment is the field of view. There are instruments that are able to observe all the skies. There are instruments that are able to have to observe at the same time a very small portion of the sky. Instrument that can be used in modes in which they can be expand a little bit the sky coverage, and that's the first point. And then you can understand this depending on where the instrument is, if it's on the satellite or the ground, that you can observe different fraction of the sky in one shot, so in one observation, or during the night or a year. If you are on the northern hemisphere, you will never see the southern sky, okay? So it's important to be able to judge figure of merit like the annual coverage. This is for an instrument that is not discussed today. There is an instrument that is able to observe this part of the sky, okay? And this is the daily throughout the year. This is its daily observation slot, okay? So it's a strip, but very big. Instrument like pointing telescope, they have to observe different spot in the sky. Okay, field of view, what else? Another point it's important to understand is the duty cycle of an instrument, okay? If you have an instrument, for example, that is working only at night, okay, then it's easy to compute. You have roughly 1,000 hours of moonless night per year. You have 9,000 hours per year. That's if everything goes well and the weather is fine, your duty cycle is 10% or less. Other instrument they can observe throughout the whole day, like Fermilab, like satellites, okay, except for maintenance or problems. But it's really when you judge an instrument, you have to think about it. Okay, so there are several things. The other things for you, if you will be in need of judging this instrument, is to learn about the data. Okay, so are the data from the instrument public or available? Sometimes they are. What is the delay in which these data are available to the scientists that are not members of the collaboration? Okay, the software, is there any instrument related software, can you analyze those data? Okay, or is there any general software that can analyze data from different instruments? The science, is there a guest observer program for the instrument for some reason? Okay. So really these things, if you need, it's really something that you have to check. And finally, in order to be able to analyze those data, you have to have a certain knowledge of the instrument. So you cannot analyze integral data without really having a certain in-depth knowledge of the instrument. And you have basically to check the things that I was saying before, effective areas and performance and so on. Okay, so these are all the ingredients for discovery, and is not available an instrument that can have them all. Okay, so you cannot maximize energy coverage, angular resolution at once. That's why you have to be patient and have many instruments that gives you pieces of information. Okay, now too many. I don't want to go into the details of this table, okay, that I was trying to start. I was trying to collect ground-based experiment, atmospheric experiment, space experiment. There are different techniques. These are past, current, and future experiment, okay? But there are some mistakes here, so please pardon this table that I was compiling. Anyhow, the message here is related to what I was saying before. It sounds strange, but we really need many of them, okay? We really need many techniques to have these full pictures of the gamma ray skies. And sometimes people think they are too many because it's really hard when you want to propose a new instrument, and I will get back to that during the presentation. It's really strange why to understand why you need that many. Okay, that's a picture, for example, from Aldo Morselli of the experiments back in 1993 when we were exploring the lowest energy. Where is the energy here? Okay, TV, MEV, and so on. That's the year we were exploring the lowest part of the energy spectrum. Now that's the scenarios here. Okay, it looks like we are sensitive throughout the whole energy part, but still, as I think I explained you before, we need to have many tools to get always the constant, the best knowledge. Okay, sometimes it makes our life experimental. It's very hard when you want to ask a new project to funding agencies. And the last message about this part is that there are some new and old tools, okay, but do not forget the importance of old tools. And I want just to cite, it's not totally related to gamma rays and the topic of this school, but I want to cite this beautiful paper from Marco and Mathieu, in which they were making constraint on primordial black holes as dark matter candidate, remembering that Voyager 1, you know, this instrument that was launched many decades ago, and now was leaving the sun. Well, sorry, the part in which the cosmic ray electrons are absorbed by the sun. Okay, they remembered that, and then they were able to make constraint by considering that now electrons below the GV are not absorbed in the heliopods. Okay, the instrument is still sending data, and it's pretty nice. They were able to resurrect the scientific interest of an instrument. So if you have ideas, you just have to check the instrument, talk with the people of the instrument, and you will maybe find new interesting things. Okay. Now we move now to discussing this different part of the spectrum. We start by the lowest energies and we go up to the highest energy. So the first things that you reach in the KeV and MEV part is that you have to go to satellites, and you have to use the Compton technique. Okay, so we are here now. This is our window for this first part. You remember this plot? We are discussing everything below from the keV to say 1 GV or a little bit less. Now, the best instrument that we have here now is really taking data, and for a long time, because it was launched in 2002, and that's a huge time for a satellite. It's Integral. Okay, Integral is making spectroscopy, so it's the understanding the energy of the gamma rays with a very good energy resolution. Okay, so E divided by the uncertainty is 500. And a pretty good angular resolution, okay, for that gamma rays. And it's sensitive to 15 keV to 10 MeV or so. As every satellite, normally, when you launch these big things, you have more than one instrument. Integral has 4 or 5. The main two for gamma rays are the spectrometer, SPI, and the imager, EBIS. Okay, I try to put links here of the instrument, but you can just Google it. Okay, and I want to mention that I will put at the end some more reference, but I didn't have time to put them today. Okay, so you see that a telescope is a satellite is a pretty complex instrument. You have the solar panels for energy, and then you have assemblies of several parts. Okay, that's what is called the payload module. For example, this is one of the two instruments. This is EBIS, EBIS here, and that's the SPI. And an additional power regulator and other instruments are there. Now, the technique that is the main detection technique here is the Compton effect. Okay, so you have a gamma rays here, and you have, we will see some dense material here. And then what you can have is a scattering of an electron that goes here. You have the gamma rays, which is reflected here, and another scattering of the electrons that you can detect. Okay, so you detect these recoils of electron in solid material. That's the Compton effect. But what is interesting, okay, of this general technique, we will see, is this part of for me at least, of the detector. So this is what is called coded mask. So Integral uses coded masks that are really a material, a mask on top of the instrument made of tiles, in which part of the tiles can transmit and part do not transmit, like absorb. Okay, and by having this this pattern here, what you do is you kind of break the correlation between the points. Okay, so here is the coding of the mask, and basically what you have is some of those pixels are able to view the source and some are blocked. Okay, so at the same time you have signal and background observable at the same time. When you observe, there is a shift on this pixel, and by the reconstruction of the image, you have basically the reduction of the background. A problem in gamma rays is that you have the gamma rays from the source, but you have all the signatures from the cosmic rays, okay? And these are everywhere. And you may remember that they are really strong. So in this way, by breaking the correlation and masking the image, you are basically able to subtract a lot of background. Okay, you will have here, there is a link in which the technique is really explained if you want to learn more about it. I'm not that familiar, I have to say, about it. Okay, but it's pretty interesting, at least to me. Now, for example, you want to know something about the SPI. Okay, so you have this coded mask we will be discussing. And then you have the germanium detector, in which the Compton is really happening. Okay, and then you have something that measures the energy deposited in these detectors. You can stop here. Okay, you can learn about the sensitivity range from 18 keV to 8 MeV. But then if you walk to the web pages of the instrument, you start to learn much more. Okay, you want to see, for example, not only the energy range, but you can measure the energy resolution here. Okay, You can measure the sky aperture, so field of view, 14 degrees, 16 degrees. This means that you know that you can observe a certain fraction of the sky. The angular resolution is pretty important, 2.5 degrees. It's a lot, okay? It's more than the moon, for example. You cannot see the moon as a point sources. What else? You have the continuum sensitivity, you have the narrow lines, because narrow line means one line is different from the continuum, and so on and so forth. Well, mass and power, maybe these things you don't need. But if you're really interested, you have to go there and try to learn more about the instrument. So that's the SPI, 18 kV, 8 MeV. This is the EBIS. Now we are 15 kV to 10 MeV. Okay, we have a little bit better energy resolution, a little bit better angular resolution, and so on and so forth. Okay, the goal of today is not to have a full understanding of this. It's really impossible. It will take several hours. I want just to give you the tools to be able to learn yourself in the future. Okay, so this actually, it's on the same instrument. There are two very similar, SPI and EBIS are kind of similar, but they are run by two collaborations, okay, in order to have really how to say, to compare the knowledge, like at LHC, in which you have CMS and Atlas running the same experiment. Okay, so again, EBIS, you have coded mask here, you have a Hooper, and then you have the solid material in which you see the Compton effect. Now, just by this, I think we can learn much better. Now this is an image of EBIS about the galactic center. Okay, so this is how you see the galactic center, and you see how what is you can guess already from here what is the angular resolution. Okay, we see the effect in which this is maybe 1 degree or so, half of a degree, and you see that we are not able to go more than that because of the angular resolution of the instrument. Okay. Okay, so integral, for example, you can download the data. The data are public, and there are portals, and you can do whatever science that you want to do, even for dark matter, if you have some ideas there. Okay. The future of this technique, if you remember, well, I will get back, but integral sensitivity is now a little bit too low. Okay, we can do much better, and the future is what is called the Astrogram or Amigo. Okay, in which we will, they will add, if done, not only the Compton part but also the pair. You remember that when you increase the energy of the gammas, the cross section for pair production is much larger than that for Compton. Okay, so you have a gamma rays, and what you have is within the tracking system the production of electron and positron pairs. Okay, which travels there by the track. Here you can reconstruct the energy of the direction of the gamma rays, and then you add the calorimeter in which you can measure now the energy very well. Okay, now, so I will spend some time on this Astrogram. It's a space mission, it's a proposed one, okay? It is not approved for some reason. You can have here the science case, and it's a very interesting document to read. The MEV, it's kind of forgotten, but it's really a part in which a lot of dark matter and fundamental physics topics are available. So I invite you, if you're curious, to have a look at those slides there. And this is the instrument. Now, I will not try, I hope I will not bother you with too many instrumental details, but the technique is always very similar. You have an instrument here in which you have the pair production or the Compton deposit of energy, which we call a tracker because we can track the source there. And on the bottom, you have the calorimeter in which you now absorb totally the particle and you measure the energy. And normally also what you have is a shield around the instrument, which gives you an anti-coincidence. Okay, you measure the cosmic rays there and the time, and then you can learn and reduce this cosmic ray background. Okay, you maybe get a little bit bored by these details, but I tell you again, and hopefully for the last time, if you want to really make a good gamma ray analysis for dark matter, it's really important you know the instrumental detail, okay, of your instrument. That's why I was saying that a histogram is really important, because this is the diffuse flux of gamma rays, okay, from GV and TV to lower energies, and there is an open window here in the MEV in which we do not measure with very good precision. That's integral, Compton, sorry, the diffuse flux. So astrogram can really say something about the MEV, and the diffuse MEV information is really important for dark matter, for example, primordial black holes, and many other things. So we hope we can close this gap very soon in the future. Now again, if you go to the documents, you find this table, figure of merits of the instrument, and as much as you read them, you try to learn something. Okay, so not only the energy bands, but you see here, for example, the field of view is now 2.5 steradians. Okay, what does it mean? Is that you really observe a huge fraction of the sky at once, which translates in the fact that you can monitor many sources. You can see what's happening out there without having to get alerted. You don't need to reposition the instrument, because you basically observe the full sky. You can, well, check the sensitivity here. What is interesting, maybe, yeah, the energy resolution. Okay, 30% for the Compton part, but 3% for the pair production part. It's really huge, 3%. This means that if you want to see a line, if you want to see a spectral shape, you can see it with this kind of instrument, okay? And so on. The sister experiment is Amigo, okay, in the US. It's basically two collaboration developing independent ideas and try to have at least one absorbed. The science reach of this instrument is really huge. Okay, you can do spectroscopy with lines because of this energy resolution. You can check the continuum, and you can even check the polarization of gamma rays, which is something that it's happening now, and we will be carrying more information. Okay, so we were on the low energies part of the satellites, MEV, say. What happened if we really enter deep into the GV regime? Now we abandon the Compton effect and we focus on the pair production, okay? So we are here. The energy is the GV and a little bit above. We had egret, the former instrument. We had more in the past, not plotted there. And we have Fermilab, okay? Fermi, it's a beautiful, it was called GLAST at the beginning, but it's a really successful experiment. I'm pretty sure you heard the name before. It won the Rossi Prize, and it's working there for more than 10 years now. Okay, yeah. And you remember past week that we were discussing about the 3 revolutions. Fermi is, together with Agile, the one that made the GeV revolution. Okay, we will get back to that part. So it's a beautiful instrument, and it's focused on this pair production technique. Now, the technique is always the same, but let's try to see a real event. So you have this instrument with an anti-coincidence shield. You have the pair conversion foil. So here is where you have the pair conversion. Then the electron and positons, when they encounter material, they are a little bit deflected. But anyhow, you can reconstruct from the 2, say, lines, the direction of the gamma rays. And then on the calorimeter, you have the deposition. So, you know, if you want to have a good regular resolution, you need to have here a good tracker, okay, for example. So a true event is this one. For example, you see here, these crosses are the tracks of the electron, and here is an image of the deposition of the energy. If you are a Fermi analyzer, really a low level, these are your events, and this is where you extract the information, okay? With a little bit more details, it's again same image as before. The anti-coincidence part is also segmented, okay? It's plastic scintillator, it's 89 of them. So you know also when the particle crossed your instrument. This is a zoom on the strip tracker, okay, here. And that's a zoom on the calorimeter, okay? It's a pretty compact instrument, if you see. I will get back to that. Okay, what I want to tell you now, I don't know, I like experiments, is that this is Fermi, okay, here. And this is before it was launched, okay? So really, when you build something like that, it's not only complex, but also you have to be sure of everything. You cannot, once it's launched, change anything, mostly anything, okay? So it's really, it must be really hard. I don't work on satellites, but it must be really hard to be tranquil in order to say, okay, now we can ship the instrument. It's so amazing, this part, and so stressing probably. And the other, for me at least, stressing part is that you cannot have a picture of your instrument while it's working. You have to just make an image unless you send a camera there to take a picture. So we don't have a picture of Fermi really in the sky. But okay, beautiful, beautiful instrument. The other message, again, because I don't know your background, is that if you really look into the details of this experiment, like, for example, the silicon strip detector of Fermi, these techniques are really something that are moving from particle physics detector. They used in balloon. You remember the balloon experiment we were discussing. So there is a strong contamination of ideas between astrophysics instrument, particle physics instrument in general, throughout the whole energy band. Okay, so it's important for us to know as much as possible of everything about the techniques. Now, just to show you the GV revolution, okay, this is egret. You remember, maybe it's a precursor of Fermi. The field of view was much smaller. There was a spark chamber here, so much wider instrument instead of the very compact. You see the very compact Fermi. You see the field of views that are makes Fermi able to detect the full sky. And by this change, you have a revolution. Okay. Okay, now we start to be boring to compare egret and LAT into the details, but then you move from this sky, okay, to a sky of Fermi with more than 5,000 targets. Okay, here you have roughly 1,000 point-like sources, a little bit more, and here you have 5,000, and you can now appreciate all the details of this. Okay, by having a good angular resolution, all this shape is possible. Okay, so really amazing, and that's when you make a revolution. Okay, that's the field of view of Fermi. That's all the sources in Fermi. There's no time to go into all the details. You see just the blue squares at the AGNs. So look how many galaxies are active in gamma rays. It's really populating the full sky. Okay. So Fermi is not alone. There is Agile that also won the Rossi Prize. It's a much smaller detector here. It's from the Italian Space Agency, and it should have been a precursor of LAT, but for some reason it was launched very late, so very close to Fermi, and so it cannot truly compete in terms of performance because of different dimension, but it's also a very successful example of an instrument that in the past and in the future you will see information from the satellite from the Chinese missions, for Chinese space agency, similar designs, but again another instrument up there. Okay, so if you're interested in those data, you may want to click there and try to see if you can get something. Now, what I want to tell you about Fermi, I want to spend a few minutes to say one thing. Well, we saw past week that now with gamma rays, what we can do is a lot of science. You see, we saw how many sources Fermi detect, and here is a list from galactic to extragalactic about the number of topics that we can study. Okay, nova explosion, supernovae, remnant. You remember past week, globular cluster, starburst galaxies, and then you go to radio galaxies, blazar, gamma ray burst, and so on and so forth. Okay, then you have dark matter searches. So, well, one person cannot do them all, cannot be expert in all of these, but really the science reach is wide. Okay, and it's wide. And what Fermi did very well and really taught us something is that Fermi prepared what is called Fermi tools. Okay, so everyone can analyze Fermi data. I think they are made available after one day, and I'm not sure, to everybody in the world. But you have tools like, scripts and program and libraries that you can access. So here's a link, for example. You can download the software, you have the documentation, you have a cicerone explain you what you have to do, and there are a lot of schools, and everything is really made easy. You have Docker, so you don't even have to install and make it that much complicated. This effort from Fermi made available the possibility for everybody, really everybody, to analyze their data. And despite the fact that what I told you before, that you have to have a good knowledge of the instrument, an example of the success of this, and it's not the only one of this thing, is that maybe some of you remember, or anyhow, there was a paper, a really interesting paper, 700 citation, if this is a measure of it, but it's more than that, by these three guys here, that published a detection of gamma ray bubbles that are now called Fermi bubbles around the galactic plane. Okay, so that's our Milky Way, and there are two bubbles here in gamma rays. We knew that they were there in X-ray, but now we know that they are there in gamma rays. Okay, so there are two pretty wide and extended over several tens of degrees bubbles. I don't want to go into the physics of this. What I want to tell you is that this was first published by non-Fermi people. Okay, of course, the Fermi people knew that there was something there, but at the end, it was published by external. And it's really important because for you, if you have good ideas, if you know what you want to look for, now you can start to be faster than the collaborations to analyze those data. Okay, so really intriguing, at least for me. Okay. Once we have left, when we want to increase the energy, okay, you remember this pay production is working, but now the instrument, the instrument itself, it's kind of 1 meter square. It's too small when you want to detect photons at very high energies. The fluxes, when you increase the energy, start to be too small for Fermi to detect. Okay, so you cannot build satellite of hundreds of square meters, at least not now, maybe in the future. And so what you have to do, you have to go back to the ground. And now it's where I know a little bit more about it. Okay. So in the ground, you see here, we have a lot of instruments, okay, everywhere in the world. Everywhere in the world, from Australia to China to Europe, everywhere. And again, do not be confused. We need all of them, okay? Well, some are old, some are not working. This one with the X, they are not working anymore. But anyhow, we need many of them to be able to have full sky coverage, full energy coverage, and so on and so forth, okay? It will be complex to learn all of them, so I will try to discuss a little bit the classes. Okay, we will have to study these slides if you want to know more after this lecture. So when we want to observe TeV photons, okay, we have to go to the ground, and then we have to make 10 telescopes. And the techniques, the leading technique is called imaging Cherenkov. Okay, we are here now we have TV photons here, and we have Hawk, Veritas, Magic, and CTA, and now Lasso to discuss. So what's happening? Why the atmosphere? Okay, we know that the atmosphere is opaque to gamma rays, luckily, because they will be really damaging our skin and body. But we know that the gamma rays, they are, as the cosmic rays, they are interacting with the medium pretty strong. Okay. So let's start with the proton, for example, a primary cosmic ray. In the atmosphere, okay, you have interaction with the atmospheric nuclei, and what you have is your pions. Okay, sometimes you have a neutral pion, and the neutral pion makes gammas. Okay, now takes these two gammas. They have sufficient energy, okay, because if you take a TV proton, you have roughly 300 GeV gamma rays, and you know that the leading interaction mechanism for at those energies is the pair production, okay? So at the end of the day, when you have a gamma, you always have pair production mechanisms. This is happening, there are some reference here, this is happening at about 30,000 meter high, 10 kilometer, 30 kilometer, is where the Concorde were flying. Okay, so also pretty dangerous for the crew. This is where I think is the maximum height, yeah, of the Hess balloon and subsequent years measurement, 9,000 meters, so pretty high. The balloons that we were discussing, they were flying up to 30 kilometers. Okay, so that's where everything is happening. Now, some of those particles, like the muons, can travel very far away from that part of the sky. This is what you call a shower of particles. Okay, from one particle you have really hundreds or several of them that can travel even laterally very far away from, from the primary cosmic rays. On the right, you have an image, I didn't put the legend, it doesn't matter, of the different shapes of the shower, okay? So that's a rough scheme. If you wanna look at the gammas, you see that it's pretty straight in its direction. I will get back to that. The proton pretty wider, this one, for example. And when you have iron, much larger atoms, you can have a very complicated atmospheric shower. But at the end of the day, what is the message here is that whatever is entering the atmosphere, you cannot detect it directly, but you can indirectly detect through something that is happening here, some of these colored lines, okay? And that's what is being done for several decades now. Okay, so a little bit more schematic. What happens if you have a cosmic ray or a gamma ray? Okay, so the cosmic ray was the image before, and we have this schematic pions production. We have the neutral pion and the gamma rays. Okay, the gamma rays are energetic, so a gamma rays can start an electromagnetic shower here and there. Okay, so pretty complicated. But then the gamma rays is this one or this one. So this one is called primary because it's really the one you want to look. It's coming from outside. This one is maybe generated within the atmosphere, so a secondary gamma ray. So this is the photons, the gamma rays that came from your supernova remnant or active galactic nuclei. When the energy is sufficient, you have an electron-positron pair here. But then the electron is, the electrons are very energetic. So they produce, during the track, they produce gamma rays by Bremsstrahlung. They radiate energy, again, still in the gamma ray band, okay? So that's Bremsstrahlung light, very energetic. And from this, again, the energy is sufficient to make another electron and positron pairs, okay? So as the particle goes down, a shower is created with every step you have more and more electrons and radiation, okay? Both for primary and for cosmic rays. An example of a development, okay, which is important to know, this development is that from one single particle, you start to have really a mess, okay? If you track everything from photons to particles, you see what you have. You have charged particles here. These are some electrons probably rotating. You have some muons that are maybe flying by, and these are other particles, okay? So it's a pretty complicated effect, but it has some regularities that can be studied. Okay, so how, at the end, how do we detect the shower, okay? Now we forget completely about what's happening outside. We have either a photon or a particle of a gamma, and now the things that the instrument detect is the shower, okay, the atmospheric shower. So first of all, about the shower, you remember that the primary cosmic rays has energies here, so there is pain production, but at a certain point, the energy of the particle shower must decrease, okay, because you multiply them until you have Compton, and then you have photoelectric effect, and this is where basically your shower dies, okay? So you multiply the particle, you divide the energy of your gamma rays goes down until they are just absorbed by matter. This means that the shower has a kind of development, a longitudinal development, in which you start with few particles, and then you have kind of a shower maximum number of particles, and then they decrease, okay? It's important this because the peak of this depends on the energy of the particle, okay? So let's look at this plot that was produced by Bruno Rossi. I want to mention Bruno Rossi because he was the founder of the institute in which I'm working now, back in the 30s of the last century, which built, he was a good experimentalist, very intuitive. It is the time of Fermi and his colleagues. And he was the first to study the air shower in details together with Greisen. So look here at the number of electrons in logarithmic scale produced by a primary particle in function of the atmospheric depth, okay? That's in radiation length. So you start with few particles and then you go up until a maximum, okay? The maximum is this maximum here. So, and then you start to decrease, and you see that the number of particles, now let's move into this direction or here, the larger the energy, the larger the energy, the larger the number of particles, okay, that's expected. But also the larger the energy, the more in depth into the atmosphere, the maximum is generated more in depth into the atmosphere, okay? So a 300 GeV particle, okay, gamma rays, yeah, produce a maximum here at about 8 atmospheric depth, okay? Now this is atmospheric depth. If you want to know, sea level is here and 2000 meter is roughly here, okay? So at 2000 meter, if you go into the mountain, you will be, you are embedded into the shower, the electrons generated by a 370 PV shower, okay, around you. The flux is not that high, but anyhow, if you know that if you go to higher mountains, these cosmic rays can even be damaging instrument, like in, you know, there is a study about Swiss train in which they travel at high altitude and the rate of failures is larger than for trains at ground. That's because of this. Okay, so this is an important piece of information to carry. If I want to see a 300 GeV photon, okay, cosmic ray, primary cosmic rays, the maximum is reached here, but if I am at 2000 meter, the number of particles is much less than what you have at higher altitude. So The question is, will I be able to detect this? And so this was thought to be impossible until this PhD student, as you are now, called Pavel Cherenkov in Russia. He was a student, and he had to study the nature of some blue lights in some material. That was the task of his thesis by his PhD tutor. Okay, he was emitting bluish light, and the study was really hard because he had to spend. Okay, there was no detector, so you have to judge these blue flashes by eye, count them by eye, and you have to kind of spend 1.5 hours in a dark cellar, okay, without light, to accommodate his eyes. Okay. At the end, he discovered that this emission was not chaotic, but it was related to particles moving into the material, track of particles. Okay, that's the birth of Cherenkov light, which I hope you studied during your courses. And some years later, Blackett suggested to use, thought that the Cherenkov light was also to be emitted in the atmosphere. Okay. Now we know that it 10 to the minus 4 of the total night sky light is made by this Cherenkov light. So let's go deeper into this. You have your particle, okay, and you know that the positrons and electrons here, they're traveling faster than the speed of light, and so they emit this Cherenkov light. If we look at this video, you have the first pair, now more pairs of electrons. Each one will Cherenkov produce light. So there will be, while the shower dies here, this light, Cherenkov light, can travel very far away at night. It can travel very far away, and if you have a detector that can measure this light, you have your detection of gamma rays. Believe it or not, this is the main technique to be able to see TV photons. So how does this work? Well, I will get back to that later, to the Cherenkov really features. But the idea is that you have to have superluminal electrons. Now, once this idea was put around in 48, I want to give you these things here. There were people that were really creative. So this Galbraith and Jelly, okay, in 1953, that's the birth of the techniques that I'm working. They took really, look at here, this is a dustbin, okay, really a pure dustbin. They put one photomultiplier tubes looking toward the bottom, in which they had a reflector here, a mirror system, and they were able to actually see these flashes of light, okay? It's not that easy because a flash of light from Cherenkov, these pictures, that blue light that was coming down, lasts only for 1 or few nanoseconds, okay? So it's really fast. That's why you don't see it at night. So the first detection was made with a dustbin and a very standard photon device, okay? So very creative. Shortly after, more of this instrument were started to go around until we reach the matureness of the stage. Now, how the Cherenkov light works, I don't want to spend too much time. I want to just tell you that, you know, it's related to the passage of charged particles in matter. That's the charged particle. The charged particle reorientate the depose moment of the surrounding material. And if the velocity of the particle is small, is smaller than c over n, the velocity of light divided by the refraction index of the medium, nothing happens. You just have these dipoles that reorientate. But if it's faster than this, then what you have is exactly the same phenomenon as the sonic boom. You have a light boom because there is a coherence between, let's say, the reorientation of the dipole. So you have not just a scramble light, but you have a coherent light front that can propagate. Okay, it's a pretty narrow light pulse of, as I said, 3 or 4 nanoseconds. This means that even if you are not able, remember this plot, to detect the particles, the electrons here, okay, you don't care because this is your shower maximum, but then you have the Cherenkov light coming from that particle, which can travel for many kilometers in the atmosphere. Okay, you have to know if you want to model it, but there's not much time. You have to model the atmospheric density. You have to model the refraction index variation in the atmosphere. You have to estimate. You can estimate the minimum energy of the electrons. At a certain point, the electron does not emit Cherenkov light anymore. Sorry to go that fast. It's 20 MeV for the 21 MeV for the electrons of the shower at sea level. What it's interesting is this part here. So the angle of emission of Cherenkov light also depends depends on the altitude. So I will go to the picture so that it's easier. This is your particle, your electron, and this is the Cherenkov light. Okay. So the Cherenkov light is emitted within a Cherenkov angle that illuminates the ground, okay? So why is that important? Because if you have an electron here, okay, how big is the area here, okay? So if you have one electron, you illuminate a circle of roughly 100, 200 meters, okay? So from one single particle, if you had a particle detector, you must be there to detect that particle. But if you want to detect Cherenkov light, your area is much wider. It's 150 meters, okay? And that's really important because automatically the area of your instrument, the effective area, is much, much larger. Okay, so that's the profile of the Cherenkov light. You have kind of a plateau of light until a maximum, and then you have this decrease of light. This can be explained by the change of the Cherenkov angle in function of the of the length. But you see, it's pretty stable. Depending on the energy, you have a circle in the ground illuminated by your 100 GeV or 5 GeV photon. Okay, which is pretty wide. Okay. Again, one should compute the amount of photons that you have to be able to reconstruct the energy, and you have to compute the fact that the light itself, sorry, this is too many information. The light, now you have light from Cherenkov, okay? What is the distribution in function of the wavelength? So look here, lambda, okay? So red and blue, well, blue, ultraviolet. The spectrum of Cherenkov photon, okay, is this red part here. So the Cherenkov effect, if you compute, is mostly on the UV part, okay, and decreasing up to the red part. But the light now is emitted at 10 kilometers, and your instrument is at 2 kilometers, and you know that light get absorbed. Now, this is optical light get absorbed in the medium by Rayleigh and Mie scattering. Okay, Rayleigh is wavelength dependent. Mie is not wavelength dependent and is due to big particles in the atmosphere. The Rayleigh scattering is just interaction with the atmospheric nuclei. And so all the UV part is absorbed, but then you have our peak. Our light, this is the light that you have to measure now to detect the shower, is peaked at 300 nanometer, which is UV. So you need to have UV blue detectors. Okay, so from this light, which is what you measure, you can explain the gamma rays that you had absorbed. Okay, we'll skip this. Again, the technique, that's the shower of particle, you forget about it because you want to know, you want to detect the Cherenkov cone. You just need to put an instrument there, okay? And then you have your Cherenkov light that is reflected on the primary and then on the secondary, and then goes to your camera, okay? So your image, the event, you remember the Fermi event, this is our event, is kind of an ellipse here in the camera of the telescope. And normally, by the analysis of this image, you go back and predict the energy of the gamma rays that was coming there. Normally, you put more than one instrument, like 2 telescopes, so that you can have a stereoscopic view and be able to better detect the event. Okay, so that's a true image. It's basically you make photographs because it's blue light, so you could do it with your telephone. The problem is that you can take roughly one picture per second, and you need to have pretty much faster because your event now it's just nanoseconds, and so you see that here is the event it's pretty short in time. Okay, so you cannot do it with your telephone. Also, the fact that we now have blue light means that we get back to be able to put mirrors and to focus the image. Okay. Again, we learned that we have to know the figure of merit of the instrument. So now we have a telescope, so we have a small field of view, 5 times 5 degrees. We cannot observe the full sky. That's the energy range. That's the effective area. Remember, 10 to the 5, 10 to the 6 meter square. Fermi, a satellite has 1 meter square. Okay, so the area of the instrument, which is the area of the Cherenkov light pool, is pretty big. That's why we can detect TV photons. But we have to observe at night, so just 1,000 hours per year. What's written in there? Okay, it doesn't matter. We have 0.1 angular resolution, 10-20% energy resolution. Okay, that's maybe too much to say. I want to tell you that here now, there is no way with this technique you can detect TV photons, but the field of view will be small. There are 3 major IACTs, imaging atmospheric Cherenkov telescopes. I hope you learn about it. HESS, MAGIC, and Veritas. I work for MAGIC here in the Canary Island. We have Veritas in the US, and we have an instrument in the Southern Hemisphere. Okay, that's it. That is HESS. Made by, look, an array of telescopes for the reason that I was saying before. Okay, I'm checking the time because I want to say something more. Okay, let me skip this. We have, if you want to learn, so for Fermi, you can do analysis. For IACT, it's a little bit more complicated to be able to open the analysis to external people because the classification of event is a little bit more complex for us. That's a gamma, regular, that's a hadron, a little bit irregular, that's background light. So we have to tag events like this. We have to check the image shape to try to understand what it is by making a random forest, a comparison with Monte Carlo, to be able to classify the event, okay? In the future, we will start to do this better and we will be able to give you access to data, okay? Let me skip this one. So this detector, I was saying also past time that they do a lot of science, galactic and extragalactic. So you really do a lot of these things. Let me skip this. The future of MAGIC, HESS, and Veritas will be CTA. I hope you have heard about it. It will be basically MAGIC, HESS, and Veritas multiplied by a factor of 10. That's the 2 MAGIC, that's a real picture. And that's CTA telescope that will be built on the around MAGIC in the Canary Islands. 19 telescopes, so a little bit less. And another array will be done in the Southern Hemisphere. Okay, why we want 2 hemispheres? Well, instruments on 2 hemispheres, now you should be able to tell. We observe a small fraction of the sky, and then we have to, in order to cover the full sky, we have to go into both hemispheres. Okay, CTA is the non plus ultra, is made of several telescopes, okay, and it will become a reality, hopefully. I removed the date because they're never true. But when you will be finishing your PhD, you could be able to have the first data from CTA. Look at the boost from MAGIC here. That's CTA, north and south. There is not only the sensitivity in the lowest energy part is much wider here. It is also better in the higher energy reach, and then you have this jump of sensitivity here. It's really much more than what we have now. Okay, let me skip this one, otherwise we do not finish. I want to tell you this part here. Okay, there is good prospects now also for dark matter. Gabi, I think, is your teacher here. She was one of the main developers of this technique. So the prospects for dark matter searches with CTA, the galactic center, are really interesting. That's dark matter cross section. That's mass, and you see that CTA is finally probing part of the parameter space. And I'm not sure if you are familiar with it. Now, CTA is much more than is MAGIC, has, and Veritas, and we will do what Fermi did. So with a tool called GammaPi, we will be giving access to the data to everybody in the world, okay? I don't know, not everything is decided, but anyhow, if you click here, now you can start learning how to analyze gamma ray data. And really, the field is changing compared to PhD student of 15 years ago. I heard you. No, I heard you. I recommended you to check these web pages. This one is for data formats for gamma ray astronomy. We are trying to finally work everybody together to have a format of data that allows an analysis of all the gamma rays data independent of the instrument. And if you want to learn more about this, there was a school past week. There is the link here, in which really there was a huge effort to teach about the coding of gamma ray astronomy. Okay, there is some link here, and it's many lectures, but I think they are still there, and you can have a look to the tools and softwares that you want to use in the future for your studies. Okay, I'm going toward the end. I have 15 minutes. I'm sorry, I have too many things to say. What happens if you go again higher and higher energies? You start to have too little photons in the ground. Okay, from not too little events, sorry, in the ground. And what you do now here in this higher energy part, so TV, many hundreds of TV and PV, you need to have particle detectors again. Okay, so you have your shower, and now you can detect the particles of the shower itself. If you have much energy, remember that the shower goes deeper into the atmosphere. So you not only detect the Cherenkov light, as we were doing now, but you detect the particles of the shower, positrons, electrons, muons, and so on. So the shower, now you can detect the shower, and normally what you have to do is there is a mountain here because you have to go higher in altitude, so not 2,000 meters, but 4,000 meters. And then you remember that the pattern of the shower is pretty wide in the field, so you have to disseminate many detectors over a certain area. But now what happens is that if you have particle detector, you don't care that if it's night or day. No, you just detect the particles, they are produced anytime. So suddenly you have a wide field of view instrument again, and you have an all-day duty cycle. Okay. Okay, this is a picture of Auger, for example, detecting the particles. How do you detect them? There are several ways in which you can detect particles. You know, there is water Cherenkov. So again, you have your particle entering some water and making Cherenkov light now in the water. You can detect the particles through scintillators or through resistive plate counters. I don't have the time to explain all those, and I won't. But now what is nice is that your instrument can be like really upon the water. Okay, so take this is a true experiment, Hawk. You take a water tank, you put some photomultipliers at the bottom, you have a charged particle entering the water, and inside the water you have, because it's that energetic, you have emission of Cherenkov light, okay? The threshold is 775 keV in water, and so you can detect your particle shower there, okay? There is either a tank, or look here, this is LASSO. You have like a very wide pond. Now it's empty, but it will be filled with water, and you put your instrument there, and that's your telescope. From the pattern of signals here, you can reconstruct the energy of your and direction of your gamma rays. Okay, I don't know if you didn't know. I was really surprised to learn that you can have telescopes in this fashion. Okay, let me skip this one and this one. Okay, so the technique now is you have your tanks, and again, this is your shower. The way in which the shower hits your detectors, like here, first in this direction and then there, the time evolution and the intensity, this is your tanks, gives you the energy of the particle. Okay, we have Hawk. Now the biggest experiment are Hawk in Mexico. It's a US and Mexico collaboration. Just to have a number, you have 300 plus 350 detectors. So these are 300, and there are many around here, detectors. So that's your telescope, and that's a building. So just to grasp the size. And we have LASSO. LASSO, it's incredible. It's so that's the that's Hawk, and that's LASSO. It's really a region disseminated with instrument. You have 5,000 scintillators, 1,000 muon detectors, 300 water Cherenkov cells at the beginning, and 12 Cherenkov telescopes. It's really a whole region disseminated with instrument. And it's really amazing what it's doing now. It's very recent, and in just less than 1 year of operation, we detected, this is the third revolution. If you remember the past lecture, we have finally, for the first time in the history, detected photons above 1 peta-electron volt. Okay, see here, the maximum energy from these guys, we have detected a photon at more than 1 PV at the ground. Okay, it was not predicted before. Okay, these are Argo. Now they do not work anymore. Precursor of Milagro, another experiment. They're not working anymore. I'm personally working now on a SWGO, Southern Wide Field Gamma Ray Observatory, besides MAGIC, which is this image that I was saying before. This will be similar to LASSO, but now LASSO is in the Northern Hemisphere, and we are not sensitive in the Southern Hemisphere. So we have to go there and build an instrument in South America. Okay, so look here, this is our idea for the moment of SWGO. This is how big LASSO is compared to the other effort in the field. Okay, so that's real power. Okay, let me also skip this. I'm going toward the end. Okay, that's the sensitivity curve again, our effort to build a better detector. This is LASSO here. Okay, and this is where we want to go with SWGO. Okay. Okay, so conclusion. Okay, I think I said already too much. I was running fast. But I was trying to give you some messages. Okay, so first of all, we need all this kind of instrument. Our knowledge of the gamma ray sky is based on all the other bands. That's an image of the same supernova remnants in 6 energy bands. You see how different it is. This we knew already. From visible to gamma rays to X-rays, we detect different things. But then when we put them together, we must have all of them to make a full picture, okay? And the TV signal, we learned that it tells us many things about what's happening at the particle level here. So we need to have a full astronomical picture of targets to be able to say certain things. And we need to have gamma rays that are probes of the astrophysics, that are probes of cosmic ray physics, as we learned, and they are probes of fundamental physics, okay, a lot. In gamma rays, we need to have also, even there, a lot of experiments for the reason that I hope I made clear today. We have different energy bands, first of all, which translates into different performance. Wide field, narrow field, again, wide field, and so on, okay? So it's important to have a full picture of what you can do with gamma rays. It's not just the energy range. If you have to do something with these, you have to know the instrument details, okay? So you have to invest some time to really know the instrument, to know the software that allows you to study the data, okay? There are some details in which you need some expert counsel. And so try and contact some members. And I think that everybody in a collaboration will be happy to teach you as much as possible about the data, okay? And finally, I mean, if you have the, so to say, the curiosity or the will, consider being participate to an experiment in the future or in your PhD, because it's really fun to build one and to translate an idea to, you know, something that you can go there and check in some cases, or not in some other cases, but still at least one, the biggest, I want to close with my PhD experience. The biggest fun that I have, okay, it was when we built Magic 2, okay, I was responsible for the mirror installation. You see here, that's a picture of us, and that's me here, finalizing the installation of Magic 2 mirrors. Okay, so with this, I want to say thank you for the patience. I spoke probably too much without pause. I want to say you goodbye, and I have a brilliant future. Thank you.
Okay, Michele, thank you so much for this super lecture on the topic. So are there questions or comments for Michele? You guys should take advantage of having this guy here today. So please go ahead. Don't be shy.
I have a question. Do you hear me?
Yeah.
I'm a little confused with respect. I understand that you explained this Cherenkov radiation and how it is produced, and what is the basically the electric particle must to have a bigger velocity than the light
Yes.
in that medium.
Exactly.
What's the relationship between that and Bremsstrahlung, or are different concepts?
So one is Bremsstrahlung is for the development of the shower. Let me go there. Yeah. Find it here. Okay. So this is, let's say, the shower, the particle shower. You have primary gamma rays. The main energy loss mechanism is pair production. Okay. But then the electron itself can radiate energy through Bremsstrahlung. Okay.
Yes.
Okay. But this mechanism here is, so to say, this is intrinsic. So it's the electron that radiates energy. The Cherenkov emission, if you want, is not the particle shower that is making it, but is the medium. So let me go now here. Okay. So you have now your electron and you have your medium around. The medium is atmospheric nuclei and molecules, okay? When the charge particle travels, you have this motion of charge, if you want. If the particle is sufficiently slow, then when the particle has passed, this dipole, so to say, goes back into the original position. There is some emission of light, but is not, so to say, doesn't have a pattern. If the particles, the electrons here, is faster than, has a velocity faster than c/n, so the medium, at a certain point, there is a regularity between the emission of radiation by reorientation of the medium, okay? And a coherence, so that's again the particle, so you have light emitted here when the particle moves, but all they produce light with the front here, okay? So it's not the electron that is radiating energy, it's the medium, if you want, that is making the Cherenkov light, okay?
Okay.
And so now if you have a front, the difference is that if you don't have a coherence pattern, you basically lose your light, okay? But like in the sonic boom, okay, you hear some strange noise, no, from an airplane if it's traveling by, but if there is a boom, you really have a coherent sudden boom, which is also intense in the sound in that case. And here you have a pattern that is able to maintain its integrity toward the ground. So at a certain point is the medium. Okay, let me also show. I was too fast here. No, but anyhow, is the medium that radiates, if you want, Cherenkov light.
The Cherenkov.
And so now this particle shower, where was it? Exactly here, for example. Now this particle at a certain point dies off at about 10 to 20 kilometers, but the Cherenkov light can propagate toward the ground. So maybe it was here, okay? So you're not able, at the end, we are not, so that's the first gamma rays, that the shower of particles. With Cherenkov telescope, we are not able to detect the shower itself, but only this blue flash that can propagate from 10 kilometers or 15 kilometers toward the ground. And if you put your telescope there, then it's where you can see it. And the other point is, remember, the pattern of these Cherenkov photons, it's over 100 meter radius over the ground. So the area of your instrument is not just the area of the telescope, but all the illuminated part, okay?
Okay. And I have another question. Could you repeat this reason behind the fact that you cannot have satellites, for instance, satellite experiments to prove higher energy photons?
Sure.
It has to do something with the reflection that you mentioned in the
No,
beginning?
well, in a certain sense, yes. Okay, so that's for me. Okay, that's really your instrument, okay? This is roughly 1 meter, okay? 1 meter area, one meter square. Now, remember, let me go back. For example, sorry, was it here? Okay. This is a true gamma ray spectrum, okay? Now, what does it mean 1 meter? 1 meter means that if you have, let me zoom, okay? That's maybe, okay, Fermi point, okay? So we go there directly. This is the first point. Here you have several photons, okay, of low energy. What is the energy? 10 to the, well, it's too narrow. Anyhow, this will be maybe 1 GeV, okay? Now, when the flux, now here, the flux, so the number of photons, higher energy, okay, diminishes very rapidly. The spectrum is 10 to the minus 3, 10 to the minus 4, okay? So Fermi would be very able to detect a photon at maybe 100 TeV, okay? The problem is that in 1 meter square, the rate of photons of 1 TeV is too small, okay? So the instrument would be sensitive, but the area of the detector is too small. There will be only 1 photon every maybe 2 years, okay?
Okay, perfect.
So it's not a technical problem, it's really intrinsic problem of the source. And you cannot do, say, a larger telescope. At the ground, it would be similar because we have 1 TeV or 100 TeV photons. It's rare, but you don't need, because of this Cherenkov light is illuminating a big fraction of the ground. It doesn't matter where you put your telescope. That would be that every time you are inside this Cherenkov pool, you detect the event. So your area goes from 1 meter square of Fermi to 10,000 meters square of magic. Okay, 10,000 meters square is the area of a circle of a radius 100 meter. Okay?
Yeah, very clear. Yes. Thanks.
Okay, thank you.
Okay, very nice. More questions or comments for Michele?
I have a very quick question. I know that you blocked out the dates of CTA, but I was wondering if you maybe had an estimate for, or maybe some more details.
Yeah.
We won't hold it to you, but I'm just interested in what you think, if there's any issues.
Sure. So, so I would say that differently, no, the CTA is similar to the dark matter case in which it's too big to fail. Okay, so at a certain point, it will be built. Now we know we have an agreement now, very recent, to be able to build a slightly smaller version of CTA than the one that I showed you before here, with a little bit less, what is it? A little bit less detectors. But I would say that the decision of everything is ready in a certain sense. So let me remove this, okay? This is what I was showing before. Beginning of operation 22 is not possible, okay? But there is already one LST telescope working and taking data. So I would say that by 2022, we will begin operation. And by 2025, you will be able, 2025, you will be able to use the first data. I'm pretty confident now on this schedule here. Okay, of course, if you are the first 2 or 3 years will be commissioning. We have to not to give just photons, but to give very well-known photons to you.
Okay, thank you.
You're welcome.
Okay, so I think we can stop here. We can take any other questions to gather down if you like in the evening. Okay, we have the coffee break now until 12:15. I remind you, you can also go to the virtual coffee break in Gather Town just in case, right? You can use it. Feel free to use it anytime. Yes, let's do that. Let's assume at 12:15. Okay. See you in a while. Thank you, Michele, once again.
Ciao, bye bye.